muscles. We get to talk about exercise and endurance and fatigue, which I think will be a good lecture. And then tonight in lab and Thursday in lab, we shift gears to the world of the nervous system. And maybe it's good, the lab's like 30 minutes long. It's like an introduction to the world of the nervous system. And then we'll go hot and heavy next week in a longer lab. But tonight's lab, Thursday's lab is kind of short. So let me first talk about a few things. I had a lot of people come upstairs before class tonight. And some of you are now starting to think about, like, what kind of grade am I going to end up with? And I think it has a lot to do with how you do on this next exam. So test 3, I said this, I think, from the beginning of the semester, the average is usually in the 80s. So you can kind of use that as an idea of kind of something to shoot for. If you said, you know, all along this semester, I've been below the class average, and you say now I want to really, you know, do really well, maybe your goal is an upper 80. I think that that's realistic. And if you've been kicking butt all along on these tests, then there's no reason why you shouldn't get an A on this test. Now, it's no easier, and it's going to be just the same length, but I think most people have figured out, you know, what it takes and what to study and what to focus on. So I think that's the reason. And I think a lot of people, I mean, look around. I mean, I think a lot of people who have been doing really poorly are no longer here. So the average for that reason also goes up. So after you take the exam on Thursday, my goal will be to have the grades, Amanda, by Saturday. Amanda texted me like 50 times. What are the grades? What are the grades? What are the grades? So I'll say Saturday, everybody. That's my goal, to have the grades by Saturday. And you might want to write this down. If you have an overall average that ends in the number 6, I think that you should be able to get the next grade higher for your final grade. So if you have an 86 or higher, then I'm expecting that you end up with an A. Okay? I mean, I'm expecting you. I'm not telling you that I think you can. I'm expecting that you will get an A. There's a lot of stuff to add at the very end of the semester that's not included right now, like attendance and mastering and extra credit and all that business. So most people have done most of that, so that's why there's a pretty significant bump at the end. So if you end up with like a 74, 75, that means mathematically it's still possible. You're just going to have to really do really well on the last remaining exams, the lab practical and the last lecture exam, which is not unrealistic, but I think to be safe, if you're in the 76 or higher, then I'm comfortable in saying that you should end up with the next higher grade. I had a student said, well, what if I have an 80 right now? You know, and I can bring it up to maybe an 83. 83, I'm going to say it's probably, you're going to end up with like an 88 or 89, which would be so sad. But if you can somehow get it up to an 84.7, get it closer to that 86, then maybe there's still hope. So take advantage of the information on this next exam. I think we've gone slow, even though it's been pretty intense, and do really well in this next test. And then we will talk. And I think that I told you that I don't think it's next week, but it's the week after. I think it's the week before our final. I'm going to sit down with each one of you in lab and kind of go over all of your grades so that the week before the final exams due, we're all on the same page. I'll say, you know, this is what I think of Kayla, this is what I think that, you know, you're going to head, this is what you need, and things like that. So there's no surprises when it comes to your final grade. Okay? So do really well on Thursday. Remember, Thursday we'll start at 5, as always, if you need that extra time. I think this test is maybe a little shorter than typically. I think you'll say that maybe that's why it's easier. Yeah. Michael, did you have a question?
Do we get the take-home test this week?
You do. It'll be posted on Blackboard on Thursday.
Cool.
So yeah, that'll be something I will also talk about. So that's something you can start working on in advance.
that something that has to be done once you start it, or can you like do a
Oh
little
my
bit
gosh,
of it,
no,
come
you
back,
can
do a
start,
little bit,
you can,
come
no,
back?
no. This is, the take-home is a list of like 20 questions. You have to type out your answers and then submit a hard copy to me on the last day of class.
Okay.
So you can work on it a little bit at a time. You can use any source, including your book, the computer. You just can't use a living source. You can't work on it in groups. You can't say, hey, I didn't get number 4, help me out with number 4, or something like that. That doesn't work. Okay, so any questions about the take-home exam and what we have remaining, the exam on Thursday? Okay. All right, so I know we've already talked about dystonia, but I want to kind of go back to this point and then move forward. So we'll finish up the last lecture and then get into today's lecture. When we talk about dystonia, we said that this was a muscular disorder in which the muscles were contracting maximally. You might remember a term that we used for a maximal contraction. We called it tetanus. So tetanus is a maximal sustained contraction. So when we look at dystonia patients, they're saying that their muscles are like alternating Charlie horses, and it never stops unless they are sleeping. And then for some reason, the muscles relax like ours do when we sleep. So what I mentioned is that what we know from dystonia patients is that it has a lot to do with the brain sending signals to those muscles to contract. So maybe some type of brain stimulation or some type of therapy with the brain could potentially calm those muscle contractions, but it's definitely something that's very disruptive. They cannot talk. It's very hard for them to move. They can walk, but it's hard for them to do that. We talked a little bit about the length of the sarcomere. This is all review, so we'll go quickly through these slides. We said that you do not have to memorize any numbers, but we said that the length of the sarcomere has to be considered optimum in order to get an optimum result. If it's overly stretched or it's overly tight, we kind of gave examples about what that would mean. You're not going to get the ultimate result. So it does kind of strengthen the idea that stretching is somewhat important before you do activities, even though it's something that I'm not a big fan of. I said that this will be on the exam on Thursday, 100%, and I said, not only do you have to kind of tell me what a muscle twitch is in the 3 parts, which is really easy, you have to utilize this graph and kind of summarize the entire sliding filament theory and make sense of it. So when we talk about latent period, we're talking about a resting membrane potential. We're talking about contraction, what happens before that, depolarization. And then in order to get the muscles contracted, we talked about, oh my gosh, did we talk about all of those different types of action potentials created using calcium and binding and creating a power stroke. And then the relaxation stage was involving release of calcium, pumping it actively pumping it back into those cisterns using ATP. Remember, ATP is used in both of those situations. And then we ended with talking about the fact that sometimes muscles are so overworked that they reach fatigue. That's going to be a big topic today. Okay, our last few slides, last class we got into the contraction strength of muscles, and it says that muscle fibers obey an all or none, which is not correct, because we know that muscle fibers can recruit different myofilaments to get the job done. I talked about lifting a full gallon of milk versus an empty gallon of milk. Use the same muscles, but you don't recruit the same muscles, right? Your body kind of says, oh, maybe I'll use some, all, whatever it takes. We looked at a figure that kind of talked about a term that will be very important once we get into the world of the nervous system. We said threshold was this kind of imaginary kind of line that says that if there's enough electrical impulse given to a muscle, it will result in a contraction. Anything below that, we've called it subthreshold stimulus. We said that there is a certain maximum of electricity that will be, or nerve signals or action potentials, whatever you want to use for that electrical energy. It says that your muscles reach a max. So you can't always say that muscles will get stronger and stronger and stronger. There is a maximum in which they peak out. Now, I think this is the slide where we ended, so we'll start here for today and go through about 4 slides, then get into today's class. When you look at this slide, this looks at multiple muscular twitches back to back with some time to relax. So you could think of this like walking very slowly, maybe doing bicep curls, kind of like this, kind of like in that rate. But then you can see that in many cases, we do muscular movements that have very little time to relax. So we get kind of like this staircase effect. Sometimes it's called TREP. And TREP leads to something that's called summation. Summation is so quick that there's almost virtually no time for the muscles to relax. And then this straight line right here represents tetanus, which is what we said dystonia patients are experiencing. A maximal sustained contraction. Maximal sustained contraction. And this line represents what happens when everything that the muscles need for contraction becomes depleted and we hit fatigue. And even though a lot of us say, well, you know, I worked in the yard and I'm really fatigued. No. That's not fatigue. Fatigue is like when your brain recognizes that you're so low in glucose and oxygen and ATP, the ingredients, that it kind of tells your mind that, man, things are not right. I feel a little dizzy. I feel like I'm going to pass out. That's fatigue. And so few of us, I think, have gotten to that point. I'll show you a video today of someone who's reaching true fatigue. Yeah, Mary?
What is an example of TREP? Like what would you do? Running?
Yeah, it'd be running fast, yeah, but not sprinting. I would say sprinting would be almost considered summation. So this would be running fast. And then once we get closer to the straight line, it'd be almost like a full out sprint. And then this line would be just like a Charlie horse, like a maximal sustained contraction. Yeah, go ahead.
You said that fatigue is when the supplies needed to do what the muscle needs to do are
Runs
not
out.
available. Is it sustained contraction or is it sustained, is it that straight line that's up there? Is that?
Yeah, so this is tetanus.
Full
So
contraction?
This means that it could, I mean, rarely do we have tetanus, you know, in a daily, in our lives. I mean, I think when we experience tetanus, it's usually, you know, sleeping or waking up after, or, you know, doing some work. So I wouldn't say that tetanus causes fatigue. I mean, you can do hours of this, or heck, you can even do hours of walking and still reach fatigue. So it's whenever the tank of oxygen and ATP and glucose run out. So this probably says that it would occur faster. In a real kind of like situation, like in labs, at Xavier, we, thank goodness I don't teach this class because I love frogs, but they dissect living frogs. Yeah, like gigantic bullfrogs. And they take their gastrocnemius muscles and they hook them up to little electrodes and they make them do everything that we talk about. They make them twitch. Their leg goes like this, you know? And then they put it full steam ahead where they cause the muscle to kind of be locked in. And then they see how long it takes for the muscle, even though they're giving it a maximal electrical stimulus, they kind of just go like this. Like, I don't care how much you're zapping me, I don't have anything left in the tank. So this is something that we rarely see. And I bet you in this room of 35 students, I bet you maybe 5 of you have really, truly felt or experienced fatigue. So we'll talk about that. Now, before we get into the physiology, I want to talk a little bit about the 2 types of muscle contractions. You may have heard of these before. for isometrics, maybe some of you do that in your workout. Isotonic. So isotonic is a reaction where we would say is more typical of any type of workout. It requires or involves both kind of elongation and contraction or shortening. It's when the muscle changes shape. That's what a isotonic muscle contraction is. But an isometric muscle contraction is that muscles don't change length, but they're still contracting, which is kind of interesting because when you think of the sliding filament theory, we said that the sarcomeres get closer together, muscles get shorter. But if I would ask you to take your really heavy backpack right now and just hold it like this, you know, that's a workout. And some of you will go, you know, like this. Or if I said, hey, go push up against that wall, push as hard as you can. Those are all you know, gosh, what's that exercise called when you're laying down?
Plank.
No, what's it called?
Planking.
Planking. That is a great example of an isometric workout. So you're just there, you're locked, and yet your muscles are contracting, but they're not changing shape. Do not worry about this graph. Don't take a picture of this graph, but this kind of represents what happens when we go through an isometric versus an isotonic. Notice that the muscle length changes in isotonic, but in isometric, as the tension increases, the length really doesn't really do anything. It stays consistent. So just be able to distinguish between the two types of contractions. Okay, so that brings us to today's lecture. And I want to show you a video that I think is pretty neat. This video deals with this video deals with a person who is doing some type of incredible exercise. He's going to swim some channel. I don't know, I can't remember, it's the English Channel or something. It's a lot. It's like days of swimming and no break. And when you see this person before he starts, you're going to say, man, that guy doesn't look like athletic. It even has a big gut. And the purpose of gaining weight, the purpose of maybe going to Olive Garden before your soccer game or whatever you did when you were in high school, and to carb load, is that you have that extra fuel in case you're doing something really, really impressive. So if you're gonna swim like 3 days or whatever this guy does, you earned going to Olive Garden and getting some for the road, whatever the deal is that they have right now. But most people who go to Olive Garden are not training to run or swim very far. So they tend to build and store that energy in long-term forms, right? We already know about that. So let's take a look at this guy. And I want you to hear about the physiology of what it takes to get this kind of activity accomplished.
Paul Hopfensberger is trying to swim 21 miles across the English Channel. As part of his training, in pounds of fat, his fat cells have grown, thickening Paul's arms, chest, and belly. It's more athletic than it sounds or looks. Our early ancestors probably looked like this. For them, fat was a vital way of storing energy.
A competitive swimmer is very much like ancient man in being constantly active and balancing their food intake with a tremendous amount of physical activity as ancient man hunted for food. So if we look at a swimmer, you'd be surprised to find that most of the fuel that they're using is really fat, both fat from the diet and fat that's stored.
As Paul heads into the frigid water, his success will depend on how he manages his body's reserves. To start with, carbohydrates from Paul's last meal, stored in the liver and muscles, quickly convert to glucose, then combine with oxygen to power him forward. Paul's muscles are now burning 3,000 calories an hour, the same number of calories in 3 large hamburgers. But after 3 miles, the easy access glucose is running out. Paul's facing a fuel crisis. It's a critical point many athletes know as the wall. It's the moment marathon runners dread.
The average person has about 2 to 3 hours worth of energy. Once that is depleted, then you have what's called hitting the wall. You just feel this physical fatigue and even this mental anguish, like you're just done, you need to stop.
The brain detects low blood sugar levels, making you feel so bad you want to quit. But to keep going, your brain has to trigger a new fuel source. To get it, the body does something astonishing. It begins to cannibalize itself, feeding off its own fat. For most of us, fat cells aren't created or destroyed. They just shrink or swell according to how much fat we're carrying. When glucose runs low, we tap fat cells for reserve energy. But fat takes longer to process than carbohydrates. That supply gap often stops runners cold. The best runners endure the process so often they're used to managing the fuel supply changeover. That lets them make it past the wall to the finish. But triumph for these guys is only a quarter of the time Paul needs to meet his challenge. Like runners, he has to switch fuel supplies and start consuming his own fat. Paul's extra layers add 60,000 calories to his fuel tank. That's 10 times the energy of the glucose his liver and muscles used when he dived in. But converting fat to fuel demands extra oxygen, straining his lungs. He's sucking in 20 gallons of air a minute, absorbed through tubes narrower than a human hair, and across tiny membranes whose total surface area is equal to half a tennis court. This burst powers Paul through 12 miles during the first 6 hours, but that's only halfway across the channel. To succeed, he'll need to keep pumping fuel to his muscles almost until nightfall. The fact is, all our bodies are engineered like Paul's. It's just that he's tuned his up through practice. Paul's training focused on improving his heart's performance.
The average person has a 5-liter cardiac output. Well, someone who's trained would put out about 35 liters of blood out of the heart, which that much more blood delivers that much more oxygen. You can make that much more energy and continue without fatigue.
So when we think of utilizing energy, that's really where we're going to start today with this class. And this slide up here talks about some activities. And I don't think you need to take a picture of this, but it talks about how do we, is it too dark or do you guys, how do we utilize energy? That means how do we utilize glucose? So when we think of most ways that we utilize glucose, it's thinking about how do we obtain that from our liver. So think back to what I talked about in the beginning of class, in the semester when I talked about carbs. And I said, when you eat a carb, whether it's bread or a baked potato or sugar, a sweet, whatever it is, it goes directly to your liver. And your liver says, okay, thank you, I'm ready to do some activity or work or some type of movement. And that's what it's intended for. But we all, I think, unless you are anti-carb, we all overdo it on carbs. And therefore the carbs then get stored into long-term storage for fat. And you can see how that can be beneficial if you're doing something really intense. So we're going to talk about doing something short, a short burst, And then we're gonna talk about how we can transition to do something, like run a marathon or swim something like that person was doing. And how do we obtain the energy to do that? Remember, it all comes from glucose. So let's start with the first part of the pathway, which involves an immediate burst. If I would say right now, there's a fire in this hallway, everybody get your stuff and just go outside, I think we could all do that by just going out this door, right behind Raven and outside. And I don't think too many of us would be breathing heavy, just moving like 50 feet. Now if I said, let's go upstairs to the 3rd floor, let's go up all these steps, the elevator's broken, some of us would not like that, right? And most of us would be breathing heavy, right? So let's talk about immediate burst. And we call that immediate burst, or that immediate use of energy. We say that we are able to do it without breathing heavy. In some cases, we don't even require oxygen. And we use enzymes. And I want you to underline these enzymes, myokinase and creatine kinase. These are 2 enzymes that are a part of a system called the phosphagen system. Encircle that. For any of you who want to go into like athletic training or something like that, you'll be talking more and more about how your muscles incorporate ATP. You can do this without oxygen, but it's a system called the phosphagen system. So on the exam on Thursday, you should be able to tell me how myokinase works, how creatine kinase works, and they both work in the exact same way. Look at this. They look for an ADP. Now let's think about this. ATP is the energy molecule, right? Adenosine tri for 3 phosphates. ADP means a di, 2 phosphates. AMP stands for mono, 1 phosphate. So look what we're doing. We're taking an A2P, a diphosphate, we're removing a phosphate, and look what we end up with, a mono. And what do we do with that phosphate? Myokinase and creatine kinase add it to an A2P to make it A3P. So basically what these enzymes do is they take a phosphate from someplace and they add it to an ADP to make it an ATP. This is like an extreme, immediate way to create energy, ATP. Because in most cases, ATP is made through glycolysis, maybe something you remember from biology that you took. So myokinase takes a phosphate away from an ADP. Creatine kinase takes a phosphate from, look, creatine, phosphate. And we end up with creatine. And that phosphate gets added to an ADP. Both enzymes create ATP. So if I say, what allows you to do something for 10 seconds? What allows you to utilize that ATP without really breathing? You're going to say the phosphagen system. But in most cases, you do something for more than 10 seconds, like 30 to 40 seconds. It says, look at this, playing basketball or baseball. You think basketball, they run more than 30 to 40 seconds. Well, no, they don't. That's one reason why my wife hates basketball, is that darn referee blows the whistle all the time. Ball goes out of bounds. Oh, foul, 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 timeout, TV timeout. So they run and then they stop. And what happens is that after about 10 seconds, they utilize, in most cases, their phosphagen system, and a new system takes over called the glycogen lactic acid system. Again, it's in the presence, or usually without a lot of oxygen. So glycogen lactic acid is also involving low to no oxygen. So you can do something for 30 seconds without really starting to breathe hard, most people. So one of the side effects when you use this system is creating an acid that causes pain. Lactic acid is the pain that causes your sides to cramp up. If you say, I want to go jog around my high school track, and think about this, because I just taught about this morning. I'm teaching like the 152 version of anatomy at Xavier in the morning. talked about chest pain associated with heart attacks. It's called angina pectoris. And it's caused by the accumulation of lactic acid in your heart. Your heart is never supposed to be without oxygen. But if there's a blockage, like heart attack, then your heart utilizes something that it's never supposed to do. And the reason why you have pain in your chest is because it's accumulating lactic acid, something that's only supposed to be associated with skeletal muscle, not cardiac muscle. So both the phosphagen system and the glycogen lactic acid is supposed to provide us with energy with little to no oxygen. Now, after we go longer, look, then all of a sudden you see after 40 seconds of intense exercise, most of us start to breathe heavy. And when we breathe heavy, we're utilizing a lot of oxygen, bringing it to our muscles. And guess what we get to do? We get to utilize that oxygen and make, look at this, 36 ATPs for every glucose molecule. Now, we never asked you to remember that phrase or number. But that takes you back to maybe biology or high school when you learned about glycolysis. Glycolysis is the process of making a ton of ATP when there is oxygen present. That's the purpose of heavy breathing, which is kind of neat. So when we think of long-term energy needs, we say we can do that as long as we have everything that we talked about earlier. For example, do we have enough energy, glucose? Do we have enough oxygen? And do we have enough electrolytes? So when we run out of that situation, we start building up weakness. Look what happens when we reach true fatigue. ATP starts to decline. The sodium and potassium pump that is used to create depolarizing and repolarizing situation starts to fail. So that means the potential, look, the resting membrane potential is no longer there. We said lactic acid builds up when we run out of those ingredients. And it could cause the cell to become very negatively charged. And that term, hyperpolarized, is a term that I won't ask you on this next test, but it will be on our final exam, because a lot of time brain activity can become hyperpolarized. That means that it becomes more negatively charged. And that neurotransmitter that is used to excite muscle, it also becomes depleted. So when you start to experience these things on the fatigue checklist, then all of a sudden your brain starts to notice, and it tries to tell you and give you symptoms and signs that it's time to stop. The best experience that I have, I've reached fatigue before, when I was running those marathons, but my wife was in a stage of her life where she wanted to run a marathon or two. I think she ran 3 or something. And so her first one was in Columbus. And it's a good one to run because it's in the fall, it's flat for the most part. And she would train for that, and she told us that she was getting ready to go, and for some reason I came up with an excuse that we couldn't go up and cheer, but secretly I was gonna take the whole family up and cheer, so I was gonna surprise her. So we got up there, she didn't think we were coming. At mile 6, we show up with signs, we're saying, "Mom, you're the woman, run, Mom, run." And she saw us and she started crying. And she was so happy to see us. Like, "Oh, I can't believe you drove all the way up here to see me run." So we just said, "Keep going, we'll see you at mile 12, So we saw her and she was waving and smiling. Then at mile 18, my kids are standing with me and we see all the people that she is like in a pack with come and go. And my youngest son, Josh, said, "Dad, where's Mom?" I said, "I have no idea." I was starting to get worried, and there she comes. And she's looking at us, and she's bawling. But she's not bawling because she's happy. She's bawling, she's saying, "There is no way I can run another 8 miles. I am done. I can't do it. I'm done. Let's go home." She was at this point where she was reaching central fatigue. Her brain was saying she was low on everything. So I took out of my backpack, a Gatorade, and gave her some things to eat. I told my oldest son, who had no idea that this was coming, he was in sweatpants and a hoodie. I said, Zach, run the last 8 with mom. He looked at me like, Dad, what are you talking about? I said, run the last 8 with mom. And so he did. And so she was able to refuel, and she finished the marathon. It was like one of her best life experiences. But at that point, her brain was telling her no way. I have a video clip of a high school runner who was like the best in the state, but when she was given different environmental kind of situations that she was used to, she also had central fatigue. Take a look at this. Now this is true fatigue.
You haven't seen the sun in like forever, so you search for a beach vacation. Sunny beaches, sandy beaches, big...
Sit back now for a study in true grit. It came on a cross-country track in Fresno, California. The state championship was on the line for a 16-year-old runner, her team, and her legendary coach. What happened there last Saturday afternoon was her gift to him.
And they are away.
Holland Reynolds is a running star, has been since the 3rd grade, racking up hundreds of miles, scores of medals. But her state championship race last Saturday was unlike any other, the race of her life. It may also be the last for her coach, Jim Tracy.
He's the greatest cross-country coach in California.
Coach Tracy is also gravely ill. In June, he was diagnosed with ALS, Lou Gehrig's disease, a condition that's sucking the strength out of his once fit muscles. For now, he can still stand on the sidelines cheering on Holland and her teammates.
The girls' Division 5.
And that's just where he was during this extraordinary race on Saturday. Unusually cold, the weather caught Holland and her body off guard. With just half a mile to go, making her move from 3rd place to 2nd, Holland hit the wall. She thought she was still running.
This is the guts that cross-country brings out in athletes.
This is very gutty here. All the way through, giving for her teammates. She's got about 30 meters to go.
993.
Look at her.
Holding her so well.
Look at her. There's the finish line.
Oh boy, about 5 meters. Hopefully
Look
she'll
at
get
that.
back up. There's a decision here. If she gets assistance, of course.
This is
decision time. They're asking her how she's feeling.
This is
If they touch her,
cross-country.
that would be disqualifier. So they're asking her, can you make it? And look at her. Such a courageous effort trying to cross that finish.
The crowd is giving her all they can here at the finish.
As soon as she crosses, they will scoop her up and take her to the medical tent right
Look
away.
at that. So she was in 3rd place, finished probably in 20th, but she still finished, right? And she had kind of that issue where her brain was saying, stop, but she overrode that kind of thing. And that can be dangerous for people who have not trained, and it can cause, usually in most marathons, you hear about this horrible situation where somebody dies because they just didn't train, and they hit the wall like this and they say, oh, I'm keep going, and they die. So it takes a lot of training to exceed and to go past that fatigue. Even the best athletes experience fatigue. I mean, you would think that, if she was going to be the 3rd in the state, she would have experienced cold and wet weather at some point, but that was just something that she hadn't maybe experienced before. And then you think of LeBron back in the day when he played for the Heat. There was a playoff game where they said that the air conditioning wasn't working, and he had to be carried off because of his cramping. So again, environmental kind of situations can play a role with fatigue as well. So what allows us to go beyond a certain time? Yeah.
I was just gonna ask, so for things like heat sinking and stuff, can those add to?
Oh, no doubt,
okay,
100%.
so fatigue.
Oh, yes, my gosh, yes. Humidity?
Yeah.
Yeah, definitely. So one of the things that we are gonna talk about is how to counter fatigue. And training, of course, is probably number 1 on the list, but making sure that we have enough carbs in the tank. And so sometimes carbs are utilized in a number of different ways, and making sure that they're readily available is a big, big deal. VO2 max is something I will not test you on because it's dealing with the respiratory system, which is something you'll hear more 2nd semester, but being able to utilize a lot of oxygen is also something you kind of progressively earn as you train. Your heart becomes stronger, you utilize more oxygen and things like that. So one of the ways that you can incorporate carbs that can be ingested quickly is by using things that you can buy at Kroger. You can buy this gel, for example, or you can buy, a form of Gatorade that has all of these necessary ingredients for building ATP. This was my go-to, and vanilla bean was my favorite flavor. It tastes like bakery cake icing. I could suck one right now. And it has like the consistency of molasses, but it's real salty and it's real sweet. And you wash it down with water, and it's supposed to give you, electrolytes that are absorbed really quickly, as well as a lot of carbs. Back in the day when my kids were younger, I used to coach them in all of the sports that they played, and I can remember one of my sons was playing in a weekend soccer tournament, and he was playing. It was really hot, and they were supposed to play 3 games in one day. And in between the games, I went to Kroger and I bought all these. These are like 5th graders, And I made them all suck one, and they all hated it. And I said, "Oh, you got to do it. It's biology, I was trying to explain to them, when you use a lot of carbs, you got to replace them, And so I was trying to give our kids a little bit of an advantage, but they didn't even like the taste of them. So I guess it's something you have to get used to. Now, when you think of breathing heavy, one of the things that I want you to put stars by in your outline is the purpose of breathing heavy. And I love all of these 4 dots, which means you'll probably have to know these for the exam on Thursday. Obviously, when we breathe heavy, we replace our oxygen reserves. So that's good. We know that myoglobin is something we mentioned being in the sarcoplasm, the oxygen binding pigment. So we replace oxygen. We also, replenish the phosphagen system. That's pretty sweet. So that phosphagen system, remember the system that's utilized first for that immediate burst of energy gets reloaded. And then, I don't know the biochemistry of this, but this seems too good to be true. It converts the pain, the lactic acid, into what? Glucose. That's amazing. So heavy breathing can take away the pain. Whoa. In fact, sometimes I can remember even when I was little playing sports, if I was cramping up, the coaches would say, put your hands above your head and, open up your chest and breathe, that kind of helps get rid of that pain. And then you can see that breathing heavy also has a lot to do with your metabolic rate, and that's more on a cellular level. These things up here are really pretty cool. Did you have a question?
You immediately answered it.
Now, when we talk about the way muscles interact with one another, we said that it was a relationship. We use terms like synergist, antagonist, remember all those terms? But today we're going to talk about the fact that we have 2 different types of muscle. We have slow and we have fast twitch muscles. And I want you to know some differences and some characteristics of each. Okay? So let's start with slow oxidative muscles, or slow twitch muscles. These are muscles that are designed to last longer, slow twitch. So they are adapted for aerobic respiration, which means they kick in better when you're breathing hard. So if you say you have great endurance in whatever movement you're doing, you're probably utilizing slow twitch fibers. For example, marathon runners who run for 3 hours or whatever are people who can utilize slow twitch fibers and not achieve fatigue. You can see that slow twitch fibers, not only do they have more mitochondria to help prevent fatigue, they have more myoglobin than your typical muscle, and they have more blood supply. Remember that, more blood supply for slow twitch. Fast glycolytic or fast twitch fibers are designed to do something impressively quick, like sprint, So they're rich, of course, in all of the enzymes that are involved with the phosphagen system. That makes sense. An immediate burst, they better be rich in those enzymes. Creatine kinase, remember, myokinase. They have a sarcoplasm reticulum, the cisterns that release calcium more quickly than your average muscle cell. Oh, that makes sense. More calcium means it binds quicker to troponin. Remember that? And so things that require a burst of activity or quick movements like eye movements, for example, these are what we call fast twitch. And one of the things down here that you can see is that the proportions, even though we all have the same muscle names, we have maybe proportions of these muscle fibers that differ from person to person in this room, thanks to our genetics. Genetics. So take a look. When you look at this table, and this is not worthy of a picture, but you can see that when we compare, for example, capillaries, something we talked about, they're more abundant in slow oxidative and less abundant. In fact, look at the color right here. They say that slow oxidative are red, and look at this, fast twitch muscles are white. Oh my God. So next time you go to KFC, and they say dark meat, white meat, you're going to say, no, I prefer fast glycolytic fibers, please. Or I love dark meat. I'll take the slow oxidative muscle fibers. So that's kind of weird, isn't it? Like if you like thighs and dark meat, those are designed to be long-term endurance muscles. But if you like breast meat, white meat, you're saying, oh, I like fast glycolytic fibers. Ew, I don't know. I'm a big carnivore, but sometimes that kind of freaks me out a little bit. Take a look at the comparison between slow oxidative and fast twitch. So it makes sense that if you're doing something for a long period of time, you're going to have more slow oxidative fibers utilizing them than maybe a sprinter. Look at a sprinter. You can see swimmers are somewhere closer to a marathon runner. So if I would show you these two pictures and I would say, all right, which one is going to win in a sprint and which one is going to win in a marathon, we all know. I mean, look at this dude. Look at all of this stuff. I mean, I want to look like him. I want to be him. But then if I said, hey, buddy, why don't you challenge this frail old person in a marathon? Guess what? This guy will kick his butt because he's designed, he is trained to become really good at sprinting, fast glycolytic. Interesting. It makes me think about the way, I guess, you know, I told you I coached soccer and I played sports and stuff like that. And I can remember when I was coaching my kids in soccer. And I wish I would have, you know, taught anatomy when I was coaching. You know, I would tell my kids, you know, before practice, okay, everybody, let's stretch, you know, whatever, stretch, you know. And then I would say, okay, let's take 2 laps around the field, you know. And so all the kids would get in a big old huddle and they run around, you know. And running long distance is nothing what they do on a soccer field, you know. You're preparing a soccer player to look like this guy. And we know from watching the World Cup, whether it's male or female, is that they are strong. They are strong. They are designed for sprinting. They're not designed to run a marathon. So that was really dumb on my part. And it made me feel even dumber when there was a year, 2003, you guys probably weren't even born then, but in 2003, I ran 3 marathons, full marathons in 1 year. And I can remember coming back from my 3rd marathon. It was in, I think I ran the Chicago Marathon. And I remember it was like in November, and some of my friends were playing indoor soccer, and they called me, they said, Mike, we need a sub. And I said, you better believe I'll be there, because I thought, well, I'm gonna show off and how fit I am. I just ran 3 marathons in 1 year. I'm coming off a marathon, I'm feeling great. I got on that indoor soccer field, which is nothing but sprints, and I was like raising my hand for a sub like within 2 minutes. Like, I need a sub. I mean, I could do this, but I wasn't ready to do this. So that's something that we need to think about. You know, someday you may coach your kid in soccer. Maybe someday you're going to train to do something. You know, whatever movement it is it Are you training only for one thing, or are you training, maybe cross-training to be overall fit? That's one of the things that I kind of want you to think about, is that this overall strength training, resistance training, endurance training, this provides us with the best overall chance of being what we would consider fit. You know, here I teach it, and I never really was into weightlifting when I was running marathons, you know, and I probably should have, you know, but I was just into aerobic. I was so happy about my resting heart rate. I was happy that I was losing weight, but I really didn't think much about strengthening my myofilaments, you know. That was last of my idea. So that's the best type of workout. It's one that utilizes both. So before we take off today, I want to talk about a few more things. And we said that this test on Thursday is the muscle test. And we said 96% of the test is dealing with skeletal muscle. So you're going to get 2 or 3 questions max from these last 2 or 3 slides. So one of the things we're going to talk about is cardiac muscle. You're going to hear more about it next semester. One of the things about cardiac muscle is that it has those intercalated discs. And intercalated discs are gap junctions, which means that we allow things to communicate quickly through them. But the coolest thing about cardiac muscle, and I've mentioned this earlier, is that cardiac muscle is designed never to reach fatigue. Thank God for that, right? So when we get tired, we take a nap, we sit down, we say, Coach, I need a sub. Our heart never gets a chance to rest, ever, ever. So it has to be designed. Look at the way it's designed. Large mitochondria, resistant to fatigue, but it's vulnerable to interruptions. And we know that when there's a blockage, whether it's maybe arteriosclerosis or something else, that it can have huge, even lethal effects. Heart attacks and cardiovascular disease is a huge killer in the United States. So disrupting the oxygen to these muscles can be a huge deal. Smooth muscle is the muscle that we said is involved with involuntary movement. Smooth muscle, you can see, does not have the striations, so it doesn't have myosin and actin. It has some other proteins, and look, it releases either acetylcholine, which is only something we talked about with skeletal muscle, or another hormone or neurotransmitter called norepinephrine, which is something that excites. We'll hear more about that next semester. So when we draw, or when we look at smooth muscle, we say that it's different from skeletal muscle in that it does not have striations, it does not have stripes. Last 2 slides before we take off today deal with some muscular issues and diseases. Muscular dystrophy. Now this is one of those diseases that has to do with a protein. There's probably 4 questions on Thursday's test talking about proteins. We know all about actin, we know about myosin, we know about titin, right? Those are 3 big proteins. But you could also add to that list something called dystrophin. We never talked about dystrophin. Dystrophin is a protein that connects, ready, the outer part of the muscle with the sarcomere. Because you might ask, why does the muscle get shorter when the sarcomeres get shorter? How does that interact with the outer part of the cell? It has everything to do with dystrophin. So people who have muscular dystrophy, you can see, are people who have problems where the dystrophin starts to become, I guess, destroyed. It's an autoimmune kind of situation. Your body's immune system starts to attack it. So that when the sarcomeres change shape, the muscles don't do anything. There's no response. So people with muscular dystrophy do not get any response. Molecularly, on a cellular level, they're changing, they're sliding, but there's no dystrophin to link them. So here you can kind of see the missing component, dystrophin, is what allows that interaction to take place. So that's the way muscular dystrophy works. And I've talked about myasthenia gravis, and I talked about my friend who, his son was on my son's basketball team, and he had no facial expression, and he, struggled with communicating, and, that was something that was really hard for him to handle. But here you can see that it is, again, another autoimmune situation where your body's naturally immune system starts to attack itself. Look what it attacks. It attacks the acetylcholine receptors in the sarcolemma. So think about that. Facial muscles and other muscles that are trying to get signals to move and contract are releasing calcium into the knob, and the knob is releasing the acetylcholine into the cleft. Everything's normal, but the receptors are gone. The body's immune system has destroyed them. So all the acetylcholine just floats in that cleft, and there's no interaction with the muscle, which means no response. Yeah, David.
Myasthenia gravis also hereditary, or?
Oh, that's a good question. That's a good question. I don't know that answer. Yeah, it's a good question, David. I don't know. Joel.
Why is it specifically on the facial muscles and not other places in the
Well,
body?
facial muscles tend to be the hot spot. I think it has something to do with kind of the nerve that that the immune system likes to affect. We're going to learn all the cranial nerves and the nerves that go from the skull to the face. For some reason are chosen, but Joel, that's another question that I don't know. I don't even know if anyone knows that answer. Those are great questions. Yeah, Jocelyn.
Why does it say for this one disease of women and the other one said like disease of men?
Yeah, it's a great idea. I mean, it's a great observation. I don't know, the person that I know as myasthenia gravis is a guy, but you can see, I guess, the majority of the people that suffer from it are either men with muscular dystrophy or women. That doesn't mean it's only men or women. Here you can see kind of like what it looks like with not being able to control facial muscles like your eyelids. People say, man, you need some sleep. Yeah, it has nothing to do with that. Okay, so that's it for our test information. Do great on Thursday. You can start at 5 o'clock as always if you want a little extra time. If you have lab, it's 6:30, so let's start at 10 till, everybody.